welcome to this problem walkthrough. Today, we'll explore an exciting problem titled Maximum XOR with an element from array. In this session, we'll break down the problem, discuss different approaches to solve it, and analyze their complexities. Stick around to sharpen your problem-solving skills. In this problem, we are given an array of non-negative integers called nums, and another array called queries. Each entry in the queries array consists of two values, x_i and m_i. Our goal is to determine, for each query, the maximum XOR value between x_i and any number in nums that is less than or equal to m_i. If no such number exists in nums that satisfies this condition, we return -1 for that query. The result for all queries is returned as an array called answer, where the ith entry corresponds to the result of the ith query. Now, the constraints on the input tell us that both nums and queries can be quite large, making it crucial to devise an efficient solution. Additionally, the values in nums, x_i, and m_i can be as large as 1 billion, which means we need to handle these large numbers effectively while adhering to the constraints. Let's look at an example to better understand the problem. Suppose nums is 0, 1, 2, 3, 4, and queries is 3, 1, 1, 3, 5, 6. For the first query, we have x equals 3 and m equals 1. Here, the valid numbers in nums are those less than or equal to 1, which are 0, 1. The maximum XOR value between x and these numbers is 3 XOR 1, which equals 3. For the second query, with x equals 1 and m equals 3, the valid numbers in nums are 0, 1, 2, 3. The maximum XOR value here is 1 XOR 2, which also equals 3. Finally, for the third query, x equals 5 and m equals 6. All elements in nums are valid since they are less than or equal to 6, and the maximum XOR value is 5 XOR 2, which equals 7. Thus, the output for this example is 3, 3, 7. Now consider another example where nums is 5, 2, 4, 6, 6, 3, and queries is 12, 4, 8, 1, 6, 3. For the first query, x equals 12 and m equals 4. However, no elements in nums are less than or equal to 4, so the result is -1. For the second query, x equals 8 and m equals 1. Again, no valid numbers exist in nums that satisfy the condition, so the result is also -1. For the third query, x equals 6 and m equals 3. The valid elements in nums are 2, 3, and the maximum XOR value is 6 XOR 3, which equals 5. Therefore, the output for this example is -1, -1, 5. These examples illustrate how the problem involves filtering numbers based on m_i and then calculating the maximum XOR for the valid subset. There are several important edge cases to consider. If all elements in nums are greater than m_i for a given query, the result for that query will be -1. Duplicate values in nums do not affect the result, as we only care about the maximum XOR value. When m_i is very large, all elements in nums are valid for that query. Additionally, if nums contains the value 0, XORing with 0 will simply return x_i. Given the large input size constraints, a naive solution that processes each query by iterating through all of nums would be too slow. To solve this efficiently, we can use a tree, or prefix tree, to store the binary representations of the numbers in nums. This allows us to calculate the maximum XOR for each query in logarithmic time relative to the number of bits in the numbers. The high-level approach involves pre-processing nums into the tree, sorting both nums and queries to minimize redundant computations, and efficiently filtering valid elements for each query while leveraging the tree to find the maximum XOR. To tackle this problem, the brute force approach is a straightforward but inefficient method. Here, for each query, x_i, m_i, we first filter the array nums to include only those numbers less than or equal to m_i. Then, for each valid number, we compute the XOR of x_i with that number and track the maximum XOR result. While this approach is simple, its time complexity is O, Q*n, where Q is the number of queries and n is the size of nums. This is because we perform filtering and XOR computations repeatedly for each query, which makes it computationally expensive for larger inputs. On the other hand, by leveraging a binary tree, we can optimize this process. The key insight is that XOR maximization favors differing bits at higher positions. For example, if a bit in x_i is 0, the best XOR result comes from pairing it with a 1 in nums. Using a tree, we can efficiently store numbers in their binary form and traverse this structure to quickly find the optimal XOR match for any query. The optimized approach begins by sorting both nums and the queries. First, we sort nums in ascending order. Then, we sort the queries based on their constraint, m_i, because smaller m_i values limit the eligible numbers in nums. This sorting allows us to process queries in a way that minimizes redundant work. Next, we use a pointer to dynamically insert numbers from nums into the tree as we process each query. For each query, x_i, m_i, we traverse the tree to find the maximum XOR value for x_i using the eligible numbers already inserted into the tree. After calculating the result for each query, we store the results in their original order. This method is significantly more efficient. The sorting steps take O, n log n plus q log q, and the tree operations, both insertion and query, are O32 per number, since integers have a maximum of 32 bits. As a result, the overall complexity of this approach is O, n plus q, *32, making it highly scalable for large inputs. When comparing the two approaches, the brute force method is much simpler to implement but struggles with efficiency, especially for large datasets. The repetitive filtering of nums and XOR computations for each query introduce a significant bottleneck. In contrast, the tree-based solution is more complex to implement but offers a dramatic improvement in speed. The pre-processing steps, such as sorting nums and queries, and dynamically managing eligible numbers in the tree, are amortized across all queries. This makes the solution fast and suitable for competitive programming scenarios. The key realization here is that by sorting nums and processing queries in the order of their m_i values, we avoid redundant work by dynamically updating the tree with only the necessary numbers. While alternatives like hash maps or segment trees were considered, they are less efficient for this problem. The tree's ability to leverage XOR properties combined with constraints on m_i makes it the ideal solution. In this problem, we're tasked with finding the maximum XOR value between a given number x_i from a query and any number in the array nums that doesn't exceed a specified limit m_i. If no such number exists, we return -1. To solve this, we can start with a brute force approach. First, we parse the input, nums as the array of integers, and queries as a list where each element contains a number x_i and a maximum permissible value m_i. We then prepare an empty result list res to store the outputs for each query. This initial setup ensures that we are ready to process the queries step by step, focusing on filtering and computing XOR values for valid numbers within the constraints of each query. To process each query, we iterate through the list of queries. For a given query, x_i, m_i, we start by filtering out numbers from nums that are greater than m_i, creating a list of valid numbers that can be XORed with x_i. Next, for each valid number, we compute the XOR value x_i XOR number and track the maximum XOR value obtained. If no valid numbers exist for the current query, we append -1 to the result list to indicate this. After processing all queries, the result list res will contain the maximum XOR values for each query. Although this approach works, it is inefficient because filtering and computing XOR for each query can become computationally expensive as nums and queries grow. To address this, we turn to an optimized approach using a tree structure. To optimize query processing, we begin by sorting the queries by their m_i values in ascending order. This ensures that we handle queries with smaller constraints first, allowing us to process numbers and nums incrementally. Additionally, we sort nums in ascending order, which makes it easier to add numbers to the tree as the constraint m_i increases. The tree is a data structure that stores binary representations of numbers, making XOR computations highly efficient. As we process each query, we only insert numbers from nums into the tree if they satisfy the condition number equals m_i. This incremental filtering ensures we always maintain a set of valid numbers for the current query. Once the tree is populated with valid numbers, we compute the maximum XOR by traversing the tree in a way that maximizes the XOR result. This involves choosing the opposite bit of x_i's current bit whenever possible. If no valid numbers exist, we append -1 to the result. After processing all queries, we return the final result list, which contains the maximum XOR values for each query in the order they were originally given. There are several key insights behind this optimized approach. First, the use of a tree allows us to compute XOR values in logarithmic time relative to the maximum number in nums, making it far more efficient than iterating through all valid numbers. Second, sorting both nums and queries ensures that we process numbers and constraints incrementally, reducing redundant computations. This incremental approach is particularly useful because once a number is added to the tree, it remains available for all subsequent queries with higher m_i. Lastly, we must handle edge cases, such as when m_i is smaller than the smallest number in nums, or when the input arrays are empty, ensuring robustness in our solution. To implement this solution, we use three key data structures. The tree is central to the algorithm, as it stores binary representations of numbers and enables efficient XOR computations. Each path in the tree corresponds to a binary sequence, allowing us to quickly identify the best number to maximize XOR for a given x_i. We also rely on sorted arrays for both nums and queries, which ensure that we can process numbers and constraints incrementally, minimizing redundant operations. Finally, the result list is a simple but essential structure for storing and returning the answers to each query. Together, these data structures work in harmony to provide an efficient and scalable solution to the problem. Now let's analyze the complexity of this optimized solution. For time complexity, sorting nums takes O, n*log, n, and sorting queries takes O, q*log, q, where n is the size of nums and q is the number of queries. Inserting numbers into the tree requires O, n*log, max_number, where max_number is the largest number in nums, since each number is represented in binary. Query processing also takes O, q*log, max_number, as we traverse the tree to compute XOR values. Combining these, the total time complexity is O, n*log, n, plus q*log, q, plus n*log, max_number, plus q*log, max_number. For space complexity, the tree requires O, n*log, max_number, to store the binary representations, and the result list takes O, q. Thus, the total space complexity is O, n*log, max_number, plus q. This analysis highlights the efficiency of the tree-based approach compared to the brute force method, making it well-suited for large inputs. Here, we start by defining the core data structures needed for this solution. First, we have the treenode class, which represents a single node in our tree. Each node has a dictionary called children to store its child nodes, and a max_number property to track the maximum number stored in the tree that passes through this node. Then, we have the tree class, which encapsulates the entire tree structure. The tree class has its own root node, which is initialized as an instance of treenode. Next, the insert method is defined to add a number into the tree. For each bit of the 32-bit integer, starting from the most significant bit, we determine the bit value either 0 or 1. If the current bit doesn't exist as a child of the current node, we create a new tree node for it. We then move down to that bit's child node and update the max_number property to ensure it reflects the maximum number seen along that path. Finally, the get_max_XOR method is introduced to compute the maximum XOR value for a given number x, provided the XOR operation involves only numbers in the tree that are less than or equal to m. If no such number exists, we immediately return -1. To maximize the XOR, we attempt to follow the path of the opposite bit at each level, as XOR is maximized when the bits differ. Now, inside the get_max_XOR method, if the opposite bit exists as a child and its max_number is less than or equal to m, we take that path, adding the corresponding bit value to our max_XOR result. If the opposite bit doesn't exist or doesn't satisfy the condition, we fall back to the current bit's path if it exists. If neither path is valid, we return -1, although this situation shouldn't occur if the tree is built correctly. Moving on to the main solution, we define the maximize XOR method in the solution class. It starts by sorting the input array nums in ascending order, as this will allow us to incrementally build the tree with numbers less than or equal to the current m value in each query. The queries are also pre-processed into a list of tuples containing x, m, and their original index, and then sorted by the m value. A tree instance is created, and we initialize a result list to store the answers for each query. Using a pointer j, we iterate through the queries. For each query, we insert numbers from nums into the tree as long as they are less than or equal to m. Once the tree is updated, we call get_max_XOR to compute the result for the current query and store it in the appropriate index of the result list. Finally, the completed result list is returned. Here, we start by defining a tree node class to represent nodes in our tree data structure. Each node has a map called children, which stores the child nodes for the binary representation of numbers. The max number property keeps track of the maximum number associated with this node. Next, we define the tree class itself. It initializes with a root node, and we implement the insert method to add numbers to the tree. The insertion process involves breaking the number into its 32-bit binary representation. For each bit, we check if the corresponding child node exists. If not, we create a new tree node. As we traverse the tree, we also update max number to ensure it always reflects the largest number seen at that node. This structure is critical for efficiently finding the maximum XOR later. The getMaxXOR method is where the magic of querying the tree happens. This method takes two inputs, x, the number for which we want to find the maximum XOR, and m, the upper limit for the numbers we can consider. We start by checking if the largest number in the tree is greater than m. If it is, we return -1 since there's no valid number to XOR with. Otherwise, we traverse the tree from the most significant bit to the least significant bit. For each bit, we try to follow the path that maximizes the XOR. This means preferring the opposite bit, as XOR gives the highest value when bits are different. However, we also ensure that the chosen path satisfies the condition that the number is less than or equal to m. If no valid path exists, we return -1, which should be rare if the tree is constructed correctly. Finally, we return the maximum XOR value we've calculated. To answer the queries efficiently, we begin by sorting the input array of numbers. Then, we prepare the queries by appending their original indices to maintain the order of results. The queries are sorted by their m values to ensure that we only consider numbers within the valid range for each query. With this setup, we initialize a tree and start processing the queries. For each query, we insert all numbers from the input array that are less than or equal to the current m into the tree. This step ensures that the tree is always populated with only the relevant numbers for the current query. As we insert numbers, we maintain a pointer, j, to avoid reprocessing the same numbers. This incremental approach significantly improves efficiency since we don't need to rebuild the tree for every query. After inserting the relevant numbers into the tree, we use the getMaxXOR method to calculate the maximum XOR for the current query. The result is stored in the result array at the original index of the query, ensuring that the output matches the order of the input queries. Once all queries are processed, we return the result array containing the answers. This approach leverages sorting, a tree, and efficient query processing to handle the problem within the constraints effectively. By carefully managing the tree and iterating through the numbers and queries in sorted order, we achieve a solution that is both fast and scalable for large inputs. To solve this problem, we start by pre-processing the input. First, we sort the array nums, so it becomes 0, 1, 2, 3, 4. This ensures that we process the numbers in ascending order. Next, we augment each query with its original index to keep track of their positions after sorting. This gives us queries equals 3, 1, 0, 1, 3, 1, 5, 6, 2. We then sort these queries based on their maximum value m, resulting in queries equals 3, 1, 0, 1, 3, 1, 5, 6, 2. After pre-processing, we initialize two key components, an empty tree data structure to store binary representations of numbers, and a result array initialized to -1, -1, -1, which will store the answers to the queries. We also initialize a pointer j to 0, which helps us iterate through the sorted nums array as we process each query. The first query we process is x equals 3 with m equals 1. To handle this, we add numbers from nums into the tree as long as they are less than or equal to m. Starting with j equals 0, we insert 0 into the tree. This involves traversing all 32 bits of the number, creating new nodes for each bit, which are all zeros in this case. Next, we insert 1 into the tree. Again, we traverse all 32 bits, creating nodes for zeros except at the last bit, which is 1. After inserting these numbers, we update j to 2, as we've added 2 numbers to the tree. Now we calculate the maximum XOR for x equals 3 using the function get_max_XOR 3, 1. While traversing the tree, we try to pick the opposite bit at each level to maximize the XOR. For most bits, we select 0 as no better option is available. At the last bit, we XOR with 1, resulting in a maximum XOR of 1. We store this result in result 0, updating the array to 1, -1, -1. Next, we process the query with x equals 1 and m equals 3. We continue adding numbers from nums into the tree where nums, j, equals m. At this point, we insert 2 into the tree, creating nodes for its binary representation. Similarly, we insert 3 into the tree, updating j to 4 since we've now added all numbers less than or equal to 3. We then calculate the maximum XOR for x equals 1 using get_max_XOR 1, 3. By traversing the tree and preferring opposite bits, we find that the optimal number yields a maximum XOR of 3. This value is stored in result 1, updating the result array to 1, 3, -1. Finally, we process the query with x equals 5 and m equals 6. From nums, we add 4 to the tree since it satisfies the condition nums, j, equals m. We update j to 5, indicating that all numbers have been processed. For this query, calling get_max_XOR 5, 6 yields a maximum XOR of 7 by traversing the tree and selecting the best possible bits. This result is stored in result 2, updating the array to 1, 3, 7. At this point, we have completed processing all the queries for the first example. The final result array is 1, 3, 7, which contains the maximum XOR values for each query in their original order. This demonstrates how the tree structure efficiently handles the XOR computation for the given constraints. Now, let's look at another example. For nums equals 5, 2, 8, and queries equals 1, 7, 10, 3, the first step is to pre-process the input. We sort the nums array to get 2, 5, 8. Then, we augment the queries with their indices, resulting in queries equals 1, 7, 0, 10, 3, 1. Sorting the queries based on m gives us queries equals 10, 3, 1, 1, 7, 0. We initialize an empty tree, the result array result equals -1, -1, and set the pointer j equals 0. For the first query with x equals 10 and m equals 3, we add numbers from nums into the tree where nums, j, equals m. Here, we insert 2 into the tree, updating j equals 1 as it's the only number satisfying the condition. We then calculate the maximum XOR for x equals 10 using get_max_XOR 10, 3. By traversing the tree and selecting the best bits, we find the maximum XOR result is 8. This value is stored in result 1, updating the array to -1, 8. Next, for the query with x equals 1 and m equals 7, we add 5 to the tree, as it satisfies nums, j, equals m. We update j equals 2, and calling get_max_XOR 1, 7 yields a maximum XOR of 6. This result is stored in result 0, updating the array to 6, 8. The final result for this example is 6, 8, completing the XOR calculations for all the queries. Here, we break down the time complexity of the solution step by step. First, we need to sort the nums array, which takes O, n log n, time due to the nature of sorting algorithms. Similarly, the queries array also needs to be sorted based on the m value, which requires O, q log q, where q is the number of queries. Next, we insert each number from nums into the tree. Since the maximum depth of the tree is fixed at 32 for 32-bit integers, each insertion takes O, 32, which simplifies to O, 1. Therefore, inserting all n numbers takes O, n. Finally, for each query, we perform a tree traversal to calculate the maximum XOR, which also takes O, 32, or O, 1, per query. With q queries, this step totals to O, q. Now, combining all these steps, we can calculate the total time complexity. Sorting nums contributes O, n log n, sorting queries adds O, q log q, tree insertions require O, n, and processing the queries takes O, q. Adding these together, the overall complexity becomes O, n log n plus q log q plus n plus q. In the worst-case scenario, where n and q are approximately equal, the dominant terms are O, n log n, and O, q log q. Hence, the total time complexity simplifies to O, n log n, which is efficient enough for large values of n and q up to 10 to the power of 5. Turning to space complexity, the main contributor is the tree. The tree stores up to n numbers, and for each number, up to 32 nodes may be used, one for each bit in the 32-bit representation. Therefore, the tree requires O, n asterisk 32, which simplifies to O, n. Additionally, we store the nums array, the sorted queries array, and the result array for storing outputs. These arrays contribute O, n, for nums and O, q, each for queries and result. When we combine these, the total space complexity is O, n, for the tree and O, n plus q, for the arrays, resulting in an overall space complexity of O, n plus q. To understand the advantage of the optimized approach, let's compare it to a brute force method. A naive solution would involve iterating through the entire nums array for each query to calculate the maximum XOR. This approach has a time complexity of O, n asterisk q, which becomes impractical for large inputs. In contrast, the tree-based solution optimizes query processing to O, q, by efficiently leveraging bitwise operations in tree traversal. This reduces the overall complexity to O, n log n plus q log q, making it feasible for large values of n and q. When we evaluate different scenarios, the best, average, and worst cases all converge to the same complexity of O, n log n plus q log q, as the number of tree insertions in query processing scales consistently. This makes the tree-based solution robust and well-suited to handle the problem constraints efficiently. When solving this problem, there are several common mistakes to avoid. First, it's crucial to handle edge cases involving the m_i values correctly. For instance, if m_i is smaller than all elements in nums, there may be no valid candidates to consider, leading to potential runtime errors. Similarly, always account for scenarios where nums might be empty or where no elements satisfy the constraints. Next, a brute force approach that checks every number in nums for each query is highly inefficient for larger inputs. This results in O, n asterisk q, complexity, which can quickly become impractical. Instead, optimized methods like using a tree or presorting the array should be explored. Another common issue is misunderstanding XOR patterns. Remember that the property XOR B equals C implies A equals B XOR C, a key insight for maximizing XOR values efficiently. Sorting also plays a vital role, but errors can occur if you sort queries by m_i but forget to process nums in ascending order. Finally, when using a tree, ignoring the maximum bit length needed can lead to either wasted memory or missing critical bits during calculations, so always ensure your tree handles the highest bit length in nums appropriately. Now let's consider interview expectations and insights for this problem. Generally, interviewers look for solutions that go beyond brute force. Implementing a tree-based approach or using a two-pointer technique after sorting demonstrates your ability to optimize and adapt your approach to constraints. Additionally, understanding and explaining XOR properties can set you apart. Being able to articulate how XOR simplifies the problem and reduces complexity is a skill interviewers value. Another important aspect is your approach to testing. Make sure to highlight how you would handle edge cases, such as queries with very small m_i values or scenarios where nums contains duplicates. Finally, be prepared to discuss trade-offs. For instance, you might explain why a tree-based solution is ideal for large datasets, while sorting combined with binary search might be more suitable for smaller inputs. Showing that you can choose and justify the most appropriate approach for different scenarios is a key part of demonstrating your problem-solving skills. Let's look at some related problems that can help deepen your understanding of the techniques involved. First, there's LeetCode 421, maximum XOR of two numbers in an array, which focuses on finding the maximum XOR value between any two numbers in a given array. This is closely tied to the current problem and also benefits from a tree-based optimization. Then, there's LeetCode 1707, which is the problem we're discussing, where you find the maximum XOR with constraints on valid elements. Additionally, LeetCode 211, Design Add and Search Words Data Structure, involves implementing a tree, making it a great exercise for mastering tree construction and traversal. Finally, LeetCode 2128, Number of Valid Words in a Puzzle, leverages bit manipulation techniques similar to what's needed for efficient XOR calculations. These problems collectively help reinforce the concepts of optimization, tree usage, and bit manipulation. There are multiple approaches to solving this problem, each with its own trade-offs. A tree-based solution is one of the most efficient. By constructing a tree for nums, you can quickly find the maximum XOR for each query in O, n asterisk log, max underscore number, plus Q asterisk log, max underscore number, time, where max underscore number is the largest number in nums. While this approach is faster for large datasets, it does require more memory to store the tree. Another option is the sort and binary search approach. Here, you first sort nums and process queries in ascending order of m_i. Using binary search or a two-pointer technique, you can identify the valid range of nums under m_i and then compute the XOR. This method has a time complexity of O, n asterisk log, n, plus Q asterisk log, n, and is easier to implement, though it may be slower for high query volumes. Lastly, there's the brute force method, which involves iterating through all elements of nums for each query to compute the XOR. While this method is simple and straightforward, it's not feasible for larger constraints due to its O, n asterisk Q, complexity. Each approach has its merits depending on the constraints and requirements of the problem. Great job following along. Today, we tackled the maximum XOR with an element from array problem, reviewed its complexities, and highlighted the importance of using tries for efficiency. Remember to practice similar problems to strengthen your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!